Great, and we are reaching our last talk, and it will be my pleasure in a minute to invite you to the stage Professor Rabia Yazicigil. She is an assistant professor of electrical and computer engineering at Boston University and visiting scholar at MIT. Her research interest lies at the interface of electronics with a specific focus on analog and radio frequency integrated circuits, signal processing, security and wireless communication, and several others. Rabia has been recipient of the number of awards, including Electrical Engineering Collaboration Research Award, and she was recently selected as a semi-finalist for 2018 35 Innovators User 35 List Sponsors at MIT Technology Review. So it's my pleasure. Rabia, please, the stage is yours.
Thank you for the introduction. Hello, everyone. I'm delighted to be here today to discuss some of the system-level security challenges that we have. Let me first find my slides before we go into details of the presentation. So I'm excited to discuss the system-level solutions for wireless security. I'm more coming from the hardware background, so my core background is designing application-specific integrated circuits, but recently I've been at the intersection of security and hardware from the systems perspective. So since you're all here, you're aware of the IoT security, why it's so critical, but typically when I give a talk to my community, hardware community, I have to emphasize why the security is so critical. So I'm going to skip the first two slides that emphasizes how the connectivity in everything brings increased security concerns. But I'm going to discuss mostly why the IoT security is hard from a system-level perspective as well as the hardware perspective. So the first reason is the resource constraints. When you have IoT devices, they are either battery-powered or energy harvesting. So it's very hard to do any kind of complex computations or even send or receive a large data packets. They're all very costly. The second concern is the massive scale of these devices. Since the number of devices is so large, then you have to have efficient and easier protocols to achieve the key management as well as have user accessibility. Most of the current solutions are actually using cloud as the trusted device so that they can achieve most of the communication via encrypted channels to cloud. The third is the physical access to devices, which creates a new attack surface. So you can actually now, as an attacker, physically tamper with the device internals as a new attack surface. Last but not least, the lack of standards is the other concern that we have that makes the IoT security hard. There is no common standard for these devices. Most of the wireless communication protocols like Bluetooth Low Energy, Zigbee, they all have their own recommendations, but they are not either entirely secure or they have complexities that are associated with them, which makes it hard to use it for these resource-constrained devices. But of course, this creates research opportunities for us, especially people from academia and industry as well, to create energy-efficient protocols, design energy-efficient circuits with security built-in, and to provide end-to-end security. So these are some of the security directions that actually I have been involved, or my colleagues, my collaborators have been involved at MIT looking at wireless power security, secure wireless communications, wireless authentication tags. So we will discuss some of the details of these works today. So as you all are aware of, the counterfeiting is a major concern for the global supply chain management. And in the past couple of years, most of the multi-million-dollar losses have been associated with the counterfeited automotive parts, aircraft parts, pharmaceutical drugs. An easy solution is to have a tag that is attached to your device. But of course now the new challenge is tag is the new target for the attacker. And embedded nature of this tag makes it actually easy to attack with physical layer attacks such as fault injection, side channel leakage. And in this work, we are basically dealing with the side channel leakage as well as power glitch attacks. the specific attack scenario that we're interested in called differential power analysis. For those of you who are not familiar with this attack, we collect multiple power traces and by varying the plain text, and we assume that the tag is using the same key. And after some number of power traces that you collected, you can correlate these traces and actually get some of the subset of your key bits. But to protect against this, in this wireless authentication tag, we never use the same key twice. So there's a key update protocol when the authentication is happening. But of course, this is quite challenging with these IoT devices, which are resource constrained, because a tag is a simple device that is passively powered by a reader. Now, actually, the reader might be hostile as well. What can happen is you can actually pause this key update protocol in the middle by interrupting your power supply. And with that, the attacker assumes that the tag will either reuse the old key or it will have to do some of the computations again and it will actually reveal some of the information about the key by redoing the computations for that cryptographic computation. So to protect against this one, we have a non-volatile memory with state backup, as well as the energy backup unit. So when you pause the operation, and if you again power it up, it will actually continue seamlessly without requiring any of the computations to be done again. So, of course, this is a nice tag, but it has one disadvantage. Of course, it has to have the secret database for the keys, which is actually not that feasible going forward. So another work that actually addresses the need for a secure database is removed by using the public key protocol is the authenticated wireless power. Here we are assuming that you have a device, IoT device, and you want to recharge this device by using a wireless charger, but of course, how do you trust this charger? It can be a counterfeited charger, and if you have a life-critical IoT device, you might actually have harsh transients that are imposed by this charger. And here, normally we typically use symmetric key protocol in these chargers, but the challenge is you have to have the keys associated with all the possible chargers that you will use that is stored on this device, which doesn't make sense because it's not scalable. Or you have to have a key exchange scheme which uses a master key that when you encounter a new charger, you have to exchange a key. But of course, if you have a master key, that's also new attack surface because it's a weak point. To overcome this, here we use a public key protocol, and charger's response is, of course, signed by the private key, is verified at the receiver, at the device, with the public key of the charger. And the interesting part of this work is this is the lowest energy-consuming public key protocol that's implemented in silicon to date. So this is actually a very low-power chip, which is also important for these resource-constrained devices. And it doesn't require any secret database to store any kind of keys. And now I'm actually going to take a deep dive into my own postdoctoral work that's focusing on secure wireless communications. Of course, it has been done with collaborations with many researchers from different backgrounds. Let me first start with defining the attack scenario that we are interested in. This is called a selective attack. And there's a real-world example. Marriott was fined recently to pay $600,000 fee by FCC because they were blocking their customers' personal hotspots, and they were trying to sell their Wi-Fi services. The reason that it's a selective attack, they were only blocking their customers' Wi-Fi spots, not everyone else's. And the reason that actually it's an interesting attack for wireless as well is this is an attack that the jammer itself, let's say it's called a selective jammer, it makes it very hard to catch. It's a sneaky attack. Jammer can actually maintain its deniability compared to broadband jamming. So in the selective jammer, you have a single victim that is targeted while the other devices around it continues their communication with no interruption in their service. And this is, as I said, the attacker can maintain its deniability, so it looks like just a packet loss over a poor wireless data link. And here we demonstrated that actually Bluetooth low energy devices that we use every day are vulnerable against these type of selective jamming attacks. On the screen, you are seeing the demo setup that we use. We have commercial Bluetooth low energy devices, a fitness device, and the headphones that are communicating with your cell phone, the BLE receiver. And this is the jammer setup, which is a very cheap and easy setup to have. And on the right side, you see the packets received by your cell phone, which is your receiver. And as you can see, we are only selectively jamming the fitness device, which actually has errors in their packets now, versus the BLE headphone communicates with no interruption in their service. Of course, this could have been a more serious attack if I was targeting BLE-enabled medical devices, but that right now I'm just using as a demonstration a fitness device and the headphones. The reason that the BLE is vulnerable to these attacks is coming from its slow hop period, we will discuss a little bit more in detail, and the individual bit location predictability. So to provide cross-tier security for the wireless communications, we actually utilize devices that are frequency agile at the device level. We develop architectures for new radios as well as protocols to communicate with a massive scale of devices. And the first challenge we address is the slow hop period. So in the Bluetooth low energy, you use packet level frequency hopping. What you do is you send each data packet on a single megahertz frequency by staying there for 612 microseconds. But guess how much time it takes for an attacker to localize the device, the data packet? It only takes 1 microsecond to localize that device. And then the attacker has 611 microseconds to jam the remainder of the packet. And that 1 microsecond number is coming from this channel bandwidth of the Bluetooth low energy communication. It's inversely proportional to that number. So in our case, we are actually proposing an ultra-fast bit level frequency hopping scheme that sends every data bit on a unique channel by changing it at the 1 microsecond hop periods. And the interesting part of this is by the time attacker localizes your frequency, you already move to a new frequency. The target transmitter only spends the minimum amount of time that's needed on a one frequency channel. And you might ask why it's hard to do, because the currently conventional hardware changes its frequencies very slowly if you want to do it in a low power fashion. I'm not going to go into details, but most of the conventional IoT hardware uses this structure to synthesize their frequencies. And if you want to use this in a low power mode, here what's interesting is it takes at least tens to thousands of microseconds to even start up that frequency synthesizer. So let's say your IoT node is in a sleep mode. To wake it up, it takes at least tens of microseconds. So we are not even close to the 1 microsecond at all. To achieve this, we utilize new devices called bulk acoustic wave devices for their frequency agility. So these are piezoelectric devices, and they have the property of being able to start up fastly, at least in the orders of microseconds. And with this, we actually remove these old hardware pieces from the conventional hardware, and we replace it with these new devices. There are other challenges that we address in the hardware level, but I'm not going to go into details. But one interesting challenge is, even though we have this new frequency agile device, we haven't achieved our goal of 1 microsecond bit level hopping yet. What happens is, you go from one frequency to another in a microsecond, but there's a settling time associated with the hardware, which is called the dead zone. So it takes at least a microsecond to settle to that frequency when you change it. So to overcome this, we actually use a ping-pong architecture. So you have two branches of this transmitter hardware that you're time interleaving. And as you can see here, now we are avoiding all the dead zones, and you can achieve your 1 microsecond bit level frequency hopping. And this was actually implemented on a chip that is designed customly. And as you can see here from the measurements, it can go from one end of the BLE communication band to other end in 1 microsecond with a 0 dead zone. But did we achieve the BLE security yet? Not. The challenge is the bit location is also leaked. The problem with the current BLE modulation schemes is when you're sending your data bit, around the carrier frequency, there's a fixed offset associated with bit 1 and the bit 0. And actually, the attacker, if it can localizes the carrier frequency, it can start overriding your individual data packet bits. So it can actually gain complete control over the data packet that you're trying to send. So it can just use that fixed carrier information to do this. And to protect against this, we proposed a cryptographically secure, data-driven, and dynamic channel selection scheme that we call a pseudo-random FSK modulation. First, I will show it from the target receiver, the base station view, and then I will also show it from the attacker perspective. Here, this IoT device is communicating with the base station, and we assume that this base station is power hungry, of course, compared to IoT devices. It's not a low power device, but it has the ability to capture the entire BLE bandwidth of 80 megahertz ISM bandwidth, and it has a pre-shared secret key between the IoT device and the base station, so it can calculate the secure channels, and it's a non-coherent detector. It means that it detects the energy to predict and decode the bit. If you look at the transmitter, what's interesting here is, in every hop, we assign a bit 0 and bit 1 a new channel. So bit 0 is designated to channel 4, and bit 1 is designated to channel 31. And in the next hop, these channels will be updated randomly. And if you're sending a bit 1, you put your energy in channel 31, and the target receiver can just decode by comparing the energy in channel 31 with respect to channel 4. But from the attacker's perspective, even though if you reveal the entire history of transmitted hops to the attacker doesn't know any location of the future bits, cannot do any better than random guessing. But on top of that, what is interesting is it actually provides data encryption in the physical layer. Let's say that the attacker can see that there is energy in this channel, but it still doesn't know if it's a bit 1 or a bit 0 without obtaining the secret key. So this provides additional data encryption in the physical layer. And this was also implemented on the chip as a cryptographically secure pseudo-random channel generator that is only dependent on your current data bit, not the past data bit or the future data bit that you are sending. And this was also implemented on that chip photo that you are seeing up there. And this is one example of a measured result. Let's say that I'm trying to send this data packet on the top, and you see the bit 0 and bit 1 locations that are randomly chosen for every hop. And in the first data bit, we are sending a bit 1, so we start at channel 14, 2.414, and then we move to the next unpredictable carrier frequency. And these are actually measured results from a hardware that we design. With low power, with the same as low power devices at Bluetooth, with additional security that's providing security in the physical layer. So this is 600 times faster than Bluetooth low energy packet level hop period, with unpredictable hopping sequence and unpredictable bit location. With that, I will also tell you a little bit about some of the new directions we are looking at. One of our work is focusing on embedded secure drug delivery. Here you can assume that you have a drug delivery system, let's say for allergy medicine or for any kind of birth control medicine that's controlled by your cell phone. And we look at how can you provide embedded drug delivery security within that IoT device that's embedded into your arm. And lately, I've been involved with providing secure packages terahertz identification tags. You might wonder, why do we want to go to very high frequencies, like above 600 gigahertz, to even build a tag? So this is actually coming from mostly being interested in the pharma fraud and providing technology against pharma fraud, which is currently the counterfeit medicine is almost 10% of the global supply chain and the global medicine trade. So current solutions are typically using either holograms or color shift inks, but that's very easy to duplicate. And you can use your traditional RFIDs, but they are large, so you can only put them on your medicine package or your bottle, but it's very easy to illegally reuse or refill those packages. So the other second sector that we're interested in is actually counterfeiting IC chips. Here, when I say counterfeiting IC chips, most of these chips come from recycling. And to avoid that, you need an embedded ID that has the encrypted data tracking and the production history of this ID itself. And what's interesting about our solution is, by going to very high frequencies, you reduce the form factor. Now the tag itself is smaller than 0.1 millimeter cube, with also integrated cryptographically secure processor that is only consuming a couple of microwatts of power. And the other interesting part of this is going to terahertz allows you to also integrate the antennas on the chip. So everything is fully integrated, so you don't need a package, which reduces the cost of the tag compared to RFID tags, because you cannot integrate the antenna on the chip for the RFID tags typically. So with this one, we are looking at all kinds of applications, going from even authenticating banknotes, because it's very small in the volume, this tag, as well as the distributed database. So just to summarize, we discussed some of the physical layer challenges and how we address them in the wireless domain. But I think what's interesting here is actually now, as researchers, engineers, we just have to learn to cross boundaries to work at the system level. We all have to learn the algorithms, devices, and the protocols to be able to provide end-to-end secure solutions, starting from physical layer to other layers of the stack. So with that, I would like to acknowledge the funding sources for these projects that I discussed, and I would be happy to take any questions that you have. Yeah, that's fine. And I'm the different background person typically. Yeah. Thank you.
Thank you, Professor Rabia. I would like to say that I'm quite concerned, not of the threats, but if things that were presented here on this session will appear as software that repair themselves automatically, and authentication speed of 1 microsecond to have the right authentication. So we should be concerned of job security to part of us here in this audience. But I think these were very important and interesting research topics and initiatives that can take us forward to all our industry. This is my opportunity to thank you all. We are at the end of a long day, and we see that really the strongest survive all this day for all the sessions and all our multidisciplinary concept of hearing, starting from law and privacy and reaching to deep technologies, including crypto, AI, and of course multi-dimension security. I would like to thank the speakers here. I would like to thank again Ilana that took care of all this day and all the arrangements. Thank you very much. And to thank you, our audience, for surviving such a day. And I hope, as myself and others, you have taken important thoughts and ideas to your cyber and other efforts in the following years. So thank you very much, and enjoy the conference.